Welcome to Ask and Learn.
Here we're trying to compress our 134A that is initially at 120 kilopascals. We are told that it's superheated by 2.3 degrees Celsius. And then it leaves at 700 kilopascals. And we're told that the second law efficiency of this compressor is 85%. So being superheated at 120 kilopascals, we can look up the saturation temperature for our 134A at 120 kilopascals, and that winds up being minus 22.32 degrees Celsius. So it's superheated up to basically minus 20 degrees Celsius. So that's the temperature at the inlet. And we can get the enthalpy and the entropy at the inlet then, looking those up or using the software. And we are told, let's see here, we want we have the isentropic efficiency, we have the second law efficiency. So let's get the isentropic or the reversible workout. Okay, so there's no heat transfer. So we're gonna get this, we're gonna assume that there's no entropy. We're gonna take the isentropic case here, where there's no entropy generated in here. So if that's the case, then we know the pressure and we know the entropy is the same as it was coming in. And so that means we can get the isentropic enthalpy of 275.79 kilojoules per kilogram. Now, the specific work is in the actual case, is the actual exit enthalpy minus the inlet enthalpy. So we don't know this yet, but in the isentropic case, or the ideal reversible case, again, because we have no heat transfer, this is all well insulated. We have the reversible work out is, we need to tack on this term here. Now, in this case, we have, so in this case, we don't know S2. No. We know, let's see here. Oh, yeah, because okay, I see what I did here. I took the, let's see here. I just basically used the exergy equation. So you can see here that we have H2 again here, right? And we have let's see here, we have H2 here, and so then we're not assuming that the S2 is S2 prime. Let's actually call this S2 prime. So that is not the case. So let's see here. Why did I let's see here. That's okay. So what we have then, so again, the exergy change. I think I could have done this in a different way. I'm assuming that maybe, hopefully, we would have got the same answer. But anyway, this is how I did it, and it may be a little bit more convoluted because I could have. Well, no, this would have given us the isentropic workout, not the reversible workout. If we would have used this, I'm not sure why I looked this up, because I don't think I ever. Oh yeah, I do use it, because down here they ask for. Oh yeah, that's why I looked it up, because down here they ask for the isentropic efficiency. Okay, so that's why I looked that up. All right, because I didn't use it here, but I do use it down here. That's why. So what we got here then is we know the second law efficiency is this guy divided by this guy, right? And we know that's 85%. So we plug everything in, and what we have here is we see that we have H2 and S2 in here. And we know the relationship between those two, but we don't know either of them. But we do know P2. And so if we knew one of these and P2, then we can know the other one. So what we need to do is basically, and the best thing to do would be use the software to play, trial and error, and say, okay, if I pick an H2, then I get an S, and I get P2, look up S2, and see how close I am, and then trial and error until I get an H2 and a pressure that gives me an entropy that gives me, that evaluates this thing to 0.85. So we can go kind of circle through that, and you kind of, see how things go, as you go up in, entropy, how does this change? And then kind of just iterate and then do some interpolation and then pick another good function and try again. So anyway, after some trial and error, we get that the enthalpy at the exit is 282.7 kilojoules per kilogram, and the entropy at the exit is 0.9773 kilojoules per kilogram Kelvin. Now, once we know these, we can figure out this and this, right? And which is what they asked for. So the actual work out, or the actual work in to this compressor is 43.88 kilojoules per kilogram. In the ideal reversible case, we would have had 37.3 kilojoules per kilogram. So we would have needed less work. Now, to figure out the isentropic efficiency, that is just for a compressor that has no heat transfer. H2 prime, the isentropic enthalpy out, minus H1 all over H2 minus H1. And so that comes out to be 84.2%. So actually very close to this. And then they want the exergy destroyed, and that's just the difference in these two guys. So that's the specific exergy destroyed. So that's 6.58 kilojoules per kilogram of exergy was destroyed in the actual process.